This should be video Organic27EBlake, and I'm trying to estimate how much stuff I can get on this video. So I'm planning to do 3 things. So if it ends early, it ends early. That probably won't happen, but. So I'm on page 73 in chapter 2. The last thing we did before stopping to do that whole redox thing, because I don't know. Somebody asked, well, how do you think of this Christmas project there, that ornament? Well, I just happened to see a video on YouTube where they had mirrored, and I thought, wow, that's a no-brainer. I'll make ornaments. So stopped what we did our section on redox, and did that lab, and now we're coming back into chapter 2. It'll be okay. Well, it was a good stopping place where we were. But we finished with 2.24. Problem 2.24 on page 73. That has nothing to do with the weeks. And now we're going to be drawing resonance structures via pattern recognition, 2.10. And there are 5 patterns of resonance structures that we need to draw. And don't let this overwhelm you. I'm not going to, ask you which one's the third one and make you draw all these all the time. It's more once you've done it for a while and you've done, a few dozen of these, you get a feel for how to do it. This would be something I'd panic on in a college organic chemistry class. But there's these 5. I want to get through these 3 on this video. So there's a allylic lone pair, allylic positive charge, lone pair adjacent to a positive charge, and then we'll try these other 2. You got a pi bond between atoms of differing electronegativity, conjugated pi bonds in a ring. So, if you turn back a couple of pages in the book to page 79, figure 2.5 and problem 2.32, you can get a picture of what it is we're doing, literally. Here are those 5 situations. And then it looks to me like, without having done this for a year, these are thrown together examples of all 5. So that's what you'd want to ultimately be able to do. But I would let you, I'm not going to really give you a test on this and have you blindly do it. But if you had this set of instructions and we filled out a worksheet that had a dozen examples like this, you should be able to do it. Okay, so this is a good book. We paid for it. Use it. I think maybe I've mentioned that, I've been poor my whole life and still poor. To get through college, you didn't have decent shoes, you didn't have decent clothes, your house is cold, barely had enough to eat sometimes. I ate rice one time for 3 weeks, so all I had to eat was a box of rice for 3 weeks. But I had textbooks, and I never griped about the cost of my textbooks. Everybody's griping about the cost of their textbooks. You know why I didn't gripe about the cost of my textbook? Because I read the stupid thing, and I worked the problems, and I used the textbook. And if I had a textbook that cost $150, and I did, which back then was like a $350 textbook now, I felt like I got my learning's worth out of it. I put the effort into the book. So use the book. And the students that griped about the cost of the book, they weren't using the book. That's why they thought it was expensive, unnecessary. Okay, so how this works is use the book. So I've got pictures out of here because they're good. We paid for it. Let's use the dang thing. If you have a double bond, the atoms involved in the double bond, which is going to be carbon, probably in all of our examples, are in a vinylic position. The word vinyl, polyvinyl chloride, PVC, we talked about this last year right before Christmas. We talked about vinyl compounds. That comes from this word. It has to do with, so if you make vinyl material, the polymers that are in there are made of something like this. Different lesson for a different day. We already did that. But vinylic positions are, in our case, the carbon atoms that are involved in that double bond. And the allylic positions are an atom removed from that, adjacent to it. In this case, these are all carbon atoms too. So what we're looking at today is the lone pairs that are in an allylic position. So as an example, let's consider this compound. It's got 2 lone pairs in it. Here's the double bond. This carbon is in an allylic position. Now it doesn't have lone pairs on it though. This nitrogen atom is in an allylic position, and it has lone pairs on it, so it would be up for discussion here. This one is just one position too far removed. It's not in an allylic position. So they give you 5 examples here. If you read the book and you worked out of it, you'll take a look at all 5, but for the purposes of keeping things rolling, I'm just going to look at this example. Let's investigate this one. So I've got it redrawn, and here's a double bond. There's an oxygen in an allylic position. Here's a carbon in an allylic position, but there's no lone pair going on here, so that nothing's going on. I can have one of those lone pairs jump down into that bond, make a double bond, and then the electron's in one of those bonds for the double bond, the ones in the pi bond, jump out and make a lone pair. And when that happens, we'll end up with a shortage of charge up here, so this ends up positive, and an excess of charge here, and this ends up negative. And we get a resonance, which is a big part of this. So it's as if this molecule has character of both of these at the same time. If you investigate this oxygen, it'll look like it's got 2 lone pairs, and it'll look like it's got positive charge. If you investigate this bond, it looks like a single bond and a double bond. If you investigate this bond, it looks like a single bond and a double bond, and it looks like there's an electron pair here with negative charge. So, all of the examples that are in the book, let's just stick to them. They're good. Going on page 75, what you need to do, we're going to pick out the double bond, atom allylic position to it, with lone pairs that are going to jump in and make a double bond here, and these have to move out. Because you can't have, the reason why that happens, you can't put a double bond here and then have 1, 2, 3, 4, 5 bonds on the carbon. Carbon doesn't do 5 bonds. Okay, so looking at example A, you got your double bond. What I should do, well, I'll leave the whole thing here. Got the double bond there. Here's an allylic position with the lone pair, so that lone pair can jump in here and make a double bond, but then electrons have to jump out of this double bond and go here on this oxygen, leaving it negative, and this will be positive formal charges. It's a resonance, so we bracket that in with the double-headed arrow showing that it has character of both at the same time. B, we're not drawing out here what looks like what's going on, but here's my double bond. That's an allylic position, so is this one, but there's nothing going on here with the double bond or anything. That's an allylic position on this carbon with a lone pair on it. That lone pair can jump into there and make a double bond, but then you can't have 5 bonds on this carbon, so electrons are going to jump out of this double bond, and then you'll have an electron pair here with a negative charge. So if you look at it, it's going to be a resonance, because now it can just, it's like it's flip-flopped. Now it can just go the other way. Okay, so this is just the opposite of this. In fact, if I flipped it over in the right angle, this is what we'd have. So it's got a resonance of this. Make sure you use a bracket for resonance and a double-headed arrow. I mean, I could draw this one without the arrows and put the double arrow over here. like this, like so. It actually could do that. This author doesn't do it that way. He doesn't have double-headed arrows, or it doesn't have the curved arrows on both configurations in the resonance, or however many there are, if there's 3 or 7 or however many. But you could. Maybe we ought to. Going on to C. Another example of, well, there's a carbon here, double bind. This oxygen is in an allylic position to it and has lone pairs. You got a carbon in an allylic position here, but it's not a player. It doesn't have lone pair. So lone pair jumps into there, makes a double bond, but electrons have to jump out of there to make onto the carbon. I got my double bond a little short, my single bond a little long, but oh well, you get the idea. Make sure you have brackets for resonance showing with the double-headed arrow. So I mean, I could draw from here down to there, and then here over to there, reverse those arrows positions. In D, here's my double bond, and everything's allylic position. This is allylic position, no lone pairs. This is in allylic position, no lone pairs. The nitrogen is in an allylic position and it has a lone pair. That lone pair can jump in here, make a double bond, but right next to it, that electrons have to jump out of that double bond and go here. When we're done, this has a positive formal charge and a negative formal charge, and we will investigate those a little harder later. Make sure you have a double-headed arrow bracket. So if you looked at this molecule, it would look like it had double bond character here and here. It would look like it had lone pair character here and here. It would look like it had charge, negative formal charge here and a positive formal charge there. And not. Okay, E. Here's my double bond, so allylic is here, nothing going on, no lone pairs, and here. So I can have a lone pair jump out of here, make a double bond, but I gotta have a lone pair jump out of the double bond and go up here. Starting out, we have a positive formal charge here and a negative one there. When we're done, we'd have a positive formal charge here and a negative one there. They look at this example a little later on. You can't have 5 bonds on this. We'll come back to that. In F, here's a double bond. This is allylic, but nothing going on. This is allylic, nothing going on. But we have a lone pair that can jump in here, make a double bond, but then electrons have to jump out of this double bond and go onto that allylic carbon. Well, this is allylic now. It wasn't allylic here. It was phenylic here. Make sure you have your brackets, double arrow. For resonance. These are all resonance. In G, here's our double bond. This is allylic. It's got lone pairs, so they can jump in here, out of here. This is what you end up with. And we have a negative formal charge when we're done there, positive formal charge when we're done there. Well, rather than just say that, maybe we'll talk about why, because it's been a while. This oxygen should end up with 8 electrons around it. And it starts with 6. So we've got 2, 4, 6, 8. But if we look at what's originally from it, there's 2, 3, 4, 5 that were owned by the oxygen. So it is stable because there's 2, 4, 6, 8 around it. But the oxygen only has 5 of its own electrons. Let's say 2, there's 1 shared there, 1 shared there, 1 shared there, which is 1 short of 6, so it's positive. Here we have 2, 4, 6, and it's sharing 1 of its electrons here, so it's got 7 of its own, so it's got a negative charge. Because that's more than the 6 it's asking for. And nothing's changing out on this end of the molecule. Make sure you got your brackets. Make sure you got your double arrow. H, nothing going on here because look, you got a double bond, so this is allylic, and this is allylic, but in those positions there's no lone pairs to play with. However, we've got a double bond here, this is allylic, again, nothing going on, but we have lone pairs in this oxygen. One of those can jump into this, make a double bond, but then electrons have to jump out of this double bond and make lone pairs. And you end up with a positive formal charge and a negative formal charge. Okay. So now, let's go on to the second thing. Allylic positive charge. Oh, by the way, allylic lone pair had 2 curved arrows. Allylic positive charge is only going to involve 1 curved arrow. Allylic positive charge. Okay, this should look familiar to you because it's the allyl carbocation on page 66 with resonance on page 67. So we've talked about this. You've seen it. So if you have a double bond here, carbon, 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 and in this allylic position, 1 carbon out or 1 atom out, there's a positive charge, allylic positive charge, then electrons can jump out of this bond and in to make a bond there. But that'll eliminate this formal charge, positive, and create one over here. And so it's got a resonance going back and forth. So we've seen this already, this exact example. Okay, so if we look at 2.26a, we've got a here's double bond. This is an allylic position, positive charge, allylic positive charge. So electrons can jump from this double bond, make one here. That alleviates this positive charge, but it creates one on over here in an allylic position. If we look at this guy, a phenyl, benzene ring, and I've got a positive charge there, short hydrogen atom, let's say, or short on electron. I can make that double bond jump over to here, but when it does, that leaves a formal charge. So it could, go back. So it appears as a resonance structure. Don't forget your brackets and double arrow on all these. Allylic positive charge. I forgot to point out that, okay, here's a double bond. This is an allylic position, but I don't have a positive charge there, or a lone pair. I do have a positive charge here. Remember, we could always put a double arrow on this. I could have the arrow going back over here and then going this way. The author doesn't do double arrows on that other one, which is fine. I said double arrows. I meant to say curved arrows. Okay, so we've got double bond here. This is allylic, but no lone pair and no positive charge. Here I've got a double bond, and this is allylic position. We got positive charge. Okay, so I can have that double bond jump here. That'll leave this positive, and I can have, and it could go right back. I've got a double bond here, and it could go over here, and that would make this positive. And then the whole thing could reverse. You can't do anything about this because from this double bond, this is the allylic position, not this one. But from this double bond, this is 1 atom out, it's allylic. So it could reverse. And don't forget to bracket it, and it does resonance with all 3 forms. So if you were to study this molecule, you would detect the appearance of what seems to be positive charge in this location, and this location, and this location, even though there's only 1 charge. Okay, and this one here, basically, it kind of chases itself around. I've got a, what is this, cycloheptene, I don't know. Just not worry about that. It's got 7 carbons, I think. 1, 2, 4, 5, 6, 7. And I've got a double bond here. And so this is allylic position to there. So I could make this chase the other way around also. But no matter what I did, if I did that, I would just end up with this guy here. So if I chased it around the other way, I'm going to end up with the same 7 answers. So let's look at this one. I've got a double bond here, a positive charge in an allylic position, so I can have that double bond, the electrons jump out of this double bond and jump into that one, leaving my positive charge here. So the same thing happens. Electrons jump out of this double bond into that one, that leaves this positive, and you can follow that around and you end up with really that positive charge. If you studied this ion, it appears to have some positive charge at every carbon atom. Bracket the whole thing, use double arrows. It's all resonance with itself. Okay. The next video will be part number 3, alone pair adjacent to a positive charge, which is this. And we'll use one curved arrow in these examples. And it's this one, lone pair adjacent to a positive charge. We'll make that go on video 27F.